Okay, this is the final frontier, so to speak. This is the last chapter. It's an optional chapter. It does come up as one of the three parts in either question 10 or 11. Not an awful lot in it. A lot of the stuff you've met before. Bit of historical fact in relation to polymers more so than anything else. But still, we might as well get the course finished completely. At least come tomorrow, we have it done. It's finished. And we can start a revision then from next week onwards. So basically, the last section looks at three things. It looks at what we call crystals. It looks at metals. And it looks at addition polymers. Okay. Now, addition polymers are better known as plastics, and the reason why they are addition polymers is because most of these plastics, they're formed by putting high pressure and high temperatures on alkene molecules, okay, things that contain a double bond. And normally what a double bond does is a double bond will open, and when a double bond opens, things can add across it. So that's why we call them addition polymers. So if you bring a lot of alkenes together and pressurize them, they all open up holding hands and form a huge big long chain, which we call modern day plastics. Okay, so let's move into the crystals first of all. Now, we all know what crystals are. Crystals are a phenomenon of nature. If there's any doubt that mathematics has a part to play in nature, you just look at a crystal. You can see the beauty of mathematics in every crystal. Okay, there are certain rules in relation to geometry and faces and so on. So if you're asked what a crystal is, okay, instead of trying to describe it in poetry, you've got to talk about it chemically. First of all, they're solids. All crystals are solid materials. Okay, the lovely thing about them also is that they have a number of faces, but the faces meet at very definite angles. So if you think of the quartz that's there in that picture, they meet at very definite angles. Okay, that means then that their organizational units inside them are arranged in a very, very special way. So first of all, to go through what we have here, crystals are, as we said, they're solids. Okay, they have a regular shape. So in the case of quartz, it's very identifiable by its shape, as are other crystals that we know and love. They have faces, as I've already said, that intersect at definite angles. So the formation of crystals are governed by the laws of geometry. Okay, and then, as we said, there's an ordered arrangement of the particles within the crystal. That's what gives it that lovely and wonderful geometry that then gives the nice refraction and gives the lovely colors and so on. Okay, so crystals, as we said, were a phenomenon, still are to this day. People still hold crystals in awe, okay, with healing powers and so on and so forth. And crystals, believe it or believe it not, are used in every manual watch, because quartz, when you put a pulse through, when you put electricity through it, it pulsates, and it pulsates to keep time. Okay, so if you ever notice on a watch, it'll say at the bottom of it quartz. That's because the crystal is what's responsible for keeping time. All right. So what's X-ray crystallography? Well, X-ray crystallography is the use of X-rays to look into a molecule, particularly a crystal molecule. And X-ray crystallography has made huge advances in the worlds of biology and in the worlds of chemistry and in the worlds of physics. Okay. And there are a number of people who use this. First of all, William and Lawrence Bragg were able to get an idea of what the structure was of these organizational units within crystals simply by taking an X-ray of the crystal itself. Now, when you take an X-ray of the human body, you get the skeleton, okay, and we can identify bones and so on. So just the way a doctor can identify bones and breakages, maybe, and disjoints and ligaments torn, these scientists could see from the pattern that came from the X-ray what way the crystal was organized. Now, what do the pictures look like? Have a look at this. That's it. Now, to you and me, that doesn't look like very much. But to the trained eye of a physicist and a chemist, they can decipher by the pattern of black versus grey versus white what the structure of the crystal actually is. Okay, so that's the art of being able to read X-ray crystallograms, if you want to call them that. All right, so when you have an X-ray crystal, you get this picture here. They can read these things. They understand what that message is. The same way as a doctor can read a skeleton from an X-ray, they can read this. Okay, so William and Lawrence Bragg were the first ones to use X-rays to determine what the internal structure of crystals were like. Now, once they were published and lauded as being successful physicists, of course it took off. And the next person to do it then was Dorothy Hodgkin. And she used X-rays to determine the structure of vitamin B12. So biologists, now that we know the structure of vitamin B12, its molecule, it's thanks to Dorothy Hodgkin. Not only did she X-ray vitamin B12, she X-rayed penicillin in solid form, and she was able to understand the molecular structure of penicillin. Okay. After that, two very important people that I know biologists will know and love, Watson and Crick. Okay. The guys who came up with the idea of the double helix for DNA. How did they come up with the idea of DNA as a double helix? From X-ray crystallography. All right. And lastly then, in 1985, which is probably the latest of all the greatest discoveries, X-ray crystallography was used in order to decipher a new structure to a molecule, something that hadn't been seen before, something that had 60 carbons, but they were all arranged in a sphere. Now, if you can picture in your head a football, leather football, and the patches on the football, some of the patches on the football are hexagons and other patches are pentagons. The way in which we put them together, that's what gives the sphere. But nature was there way before the leather football was. And it did exactly the same thing with carbons. Made hexagons with carbons, made pentagons of carbons, put them together and formed a perfect sphere. But it wasn't until 1985 when a guy called Buckminster Fuller, don't know what his first name was, but Buckminster Fuller was his surname. Lovely name. Yeah, typical of all Americans, they got wonderful names, surnames with about 60 letters in them. Anyway, Buckminster Fuller. So Mr. Buckminster Fuller used X-rays in order to look into the crystal of this particular allotrope of carbon. Now, an allotrope is a different physical form of the same element, okay? Talk about that in a few moments. So he looked into this allotrope of carbon and he was amazed to see that these 60 carbons had arranged themselves into a perfect sphere by alternating hexagons with pentagons and hexagons with pentagons. They got a perfect sphere, and they simply called it Buckminster Fullerene. That's the name of the chemical. That's an allotrope of carbon. I'll show you what it looks like in a moment. So, Buckminster Fullerene, just before we go on, short name buckyballs. Okay, and what they are is they're cages. They're spherical cages. Now, one of the great things about these is that they can carry chemicals around the human body to direct sites. So therefore, instead of giving people chemotherapy that goes right through the body and destroys good cells and bad cells alike, it may be possible in the future that we can take these little spheres of Buckminster Fullerene, inject them with chemotherapy and direct them directly to the tumour, where they will deliver then the toxic chemicals and kill the tumour itself, while the rest of the human body is completely unaware of what's going on. Okay, that would be revolutionary in terms of chemotherapy, but it will happen. That's the nanochemistry that's going on at the moment in terms of the medical field. So what type of crystals do we have? Well, first of all, we have what are called ionic crystals. Okay, now this big grid that's in front of you on this slide here, you do have to know this. This is a grid that you have to learn off, but most of this stuff you already know. Think about the first line. If a crystal is ionic, then the particles that the crystal are made up of are ions. Okay, and if the particles in the crystals are ions, they're being held together by electrostatic attraction. And if they're being held together by electrostatic attraction, they're going to give you quite tough, durable solids with a very high melting point. Okay, they would be extremely hard, but because they contain charged particles, if we melt them or put them into water, they will be able to conduct the electricity. All right, that's it. And you know that stuff already. But that's the first line. Watch it again. An ionic crystal has ions in it, which are held together by electrostatic attraction, giving you a very, very hard solid, therefore, with a high melting point. And because they contain ions, they will dissolve in water, or they will be molten, and they will conduct electricity. All that. Okay, so you know the first line. Now, let's see if we can move on to the next one. See if we can move on to the molecular crystals. And the name itself suggests what they are. A molecular crystal is a crystal whose individual points in it are made of molecules. So with the ionic crystal, the individual reference points in the crystal are ions. In a molecular crystal, the individual reference points in the crystal are molecules, things like maybe CO2. And the reason I'm talking about carbon dioxide is because we can use carbon dioxide in the lab. It's what comes out of the fire extinguisher, okay? That dry ice. That is a solid, it's a crystal, but it's a crystal of CO2. So the lattice points, or the reference points within the crystal, are molecules of CO2. Now, carbon dioxide is a covalent substance. So that means that if the reference point in the crystals are molecules, then the forces within the crystal will be very weak van der Waals forces. That's all, because they're covalent substances lying side by side. Okay, so there'll be van der Waals forces. What does that mean? That means then that they'll be very, very soft, either soft solids, liquids, or even gases, or the crystals are very soft solids. Okay, Usually these things are liquids or gases, so you know about carbon dioxide, but when they're in crystal form, they're very soft, which means they melt easy, okay? If the reference points are molecules, covalent molecules, there's no ions present. So therefore, they won't dissolve in water and they will not conduct electricity. That's row number 2. Look at it. Molecular crystals, what does it mean? Their reference points are molecules. Molecules are covalent, so they're held together by van der Waals forces. Van der Waals forces give us very soft solids that will melt easy, and because there's no ions present, there will be no conductivity of electricity and no dissolving in water. But what they will dissolve in is cyclohexane. So you can dissolve I2 crystals, iodine crystals, they'll dissolve perfectly in cyclohexane, but they will not dissolve in water. Okay, next one. A macromolecular crystal. Now the name suggests it all. A macromolecular crystal is a crystal made of one huge molecule. And what comes to mind is a diamond. Okay, and I'll show you what diamond looks like in a moment. Or Buckminster fullerene, or one of these things that is made up from a huge number of carbons. But diamond is the one I want you to focus on. Now, if you have within this particular macromolecule reference points of the same element, then it really is an elemental crystal. Okay, it's a pure crystal, which means then that the crystal is one huge big molecule with atoms at the reference points. And if you have the same atoms in that crystal, you'll get something like carbon, 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 all joined together in a diamond. That's going to be covalent. And if there are covalent bonds between them, well then what will happen is these covalent bonds, if they're all built up into one huge big lattice structure, will form a rigid skeleton that is so strong that you'll end up with substances that are the hardest substances known on Earth. So I'm talking about the diamond, okay? And the reason why the diamond is so hard is because it's one molecule made up of carbons which are linked to every other carbon around it by 4 bonds. And that builds up into a huge lattice which gives super strength to that particular molecule, which is the crystal itself, and therefore we get something that is the hardest species known on Earth. Because it's so hard, its melting point is going to be abnormally high, but 4,000 degrees before you can melt a diamond. Okay, and because it's so hard, it is not going to conduct electricity because there's nothing in there that can move. It's all locked in, huge big molecule. And lastly, then you throw a diamond into water, it ain't going to dissolve, thankfully. Yeah, if you're washing your hands and you're wearing a lovely big diamond engagement ring, your diamond isn't going to fall away or dissolve or melt. It can't. So therefore, with macromolecules, particularly like the diamond, what do we know about them? They are crystals of one molecule. They are atoms of the same element. Therefore, they're all covalent. Because it's a huge covalent, here we are here, it's macromolecules. It's a crystal, is one big molecule made up of covalent bonds. But because they're covalent bonds, they will make a huge rigid lattice structure that will only melt at about 3,500 degrees. Because it's a massive molecule, there's no free ions. Therefore, there will be no solubility. Okay, and again, as we said, it'll be extremely hard. The hardest substance known on Earth. And I keep asking this question, I know, how do you cut a diamond? Answer, with another diamond, because there's nothing harder than the diamond. And lastly, then you've got your metallic crystals. Now, as the name suggests, they're metals. Okay, and we've just studied metals in the previous chapter. So what we do know about metals is this: metals have a tendency to lose electrons. Okay, the ones at the top of the activity series, their electrochemical series, they lose electrons. Ones lower down, well, they lose them if they're pushed, but they're quite big and quite lazy, so they're not going to lose them that readily. But all metals have a tendency to lose electrons, which means if you have a crystal made of a metal, there could be electrons in there that are willing to move. See? And if they're willing to move, that means metal crystals can conduct electricity. So let's go down through the last line here. Metal crystals will have as the reference points in the crystal metal ions. So K plus, Na plus, whatever they're going to be. So we had the 3 metals in junior cert: sodium, lithium and potassium. And I was able to take out those metals because they were metallic crystals. And in those metallic crystals were only atoms of sodium or potassium or lithium. All right, which means that if they're only metal ions, these metal reference points, they can send out electrons, meaning that you can have a sea of electrons in there ready to move as soon as you put an electric current through it. And if that's the case, then they will conduct electricity. Okay, But because of the fact, and read this one here, because of the fact that metal ions are different in size, their melting points will differ enormously. Now, if you remember, potassium we can squish. Yeah, we can actually squish it. Mercury is a metal, but it's a liquid at room temperature. Gold is a very, very hard precious metal that remains a hard precious metal for very, very high temperatures. So there's a huge variation in melting points. Hardness, as we said, no general rule. Melting point, all over the place. Electrical conductivity, huge, because all metals tend to lose electrons. So yes, they will conduct electricity. Copper, the best conductor we have. Are they soluble in water? No, they corrode, but they're not soluble in water. Okay, if you put them into acids, only the metals above hydrogen in the activity series will react with the acid. The ones below won't. So poor spelling can mean absolute zero. From anything from potassium down to iron, or down to lead, I should say, they'll all react with acid, liberating hydrogen and forming salts. Whereas the metals below that, chemistry, math, science and geography, copper, mercury, silver and gold, they won't dissolve in acid. Okay, so that table, even though it looks quite complex, is in fact quite logic. So again, take each line as they are, think about what the crystal is, and from what the crystal is, think about the units it has, think about how those units are attracted to one another, think about the force of attraction, whether it makes them into tight solids or kind of a squishy solid, and then think in terms of conductivity and solubility. Okay, so as I told you already, an allotrope. Now I don't think we've met this word before. We've met isotopes. Isotopes are atoms of the same element having the same number of electrons and protons and different numbers of neutrons. But an allotrope is nothing more than a different physical form of the same element. Now I just want you to think of carbon. Carbon can exist as the soot that you know in your chimney. Okay, carbon can also exist as diamond. It's a macromolecule. It's a huge big framework of just carbon atoms all joined to each other. Very, very rigid structure. Hardest substance known on Earth. Okay, but the middle one then is graphite. It's what's in your pencil. What we used to call it the lead in the pencil. It's not lead. If it was lead, we'd all be dead from chewing pencils. But it's not lead. It's graphite. And graphite, when you bring it over paper, leaves a mark behind because of the way that its molecules are structured. So there's three in particular that I want you to remember. There is carbon itself. Then there is the diamond. There is the graphite, and there is the Buckminster fullerene. Okay, so they're the three I want you to think of. Diamond, hardest substance known on Earth, only made of carbon atoms. Graphite is a soft, slippery substance, only made of carbon. Buckminster fullerene is a sphere arranged of 60 carbons, arranged in hexagons and pentagons, giving a perfect sphere, which is very different from the other two. So different physical forms of the same element. That's what we're dealing in relation to that. Whoops, sorry. Get rid of that. No. Just want to get rid of the writing there. Okay, so that's allotropes. Now, as we said already, carbon has many different physical forms, and these different physical forms are called allotropes. Different, that's the definition. Different physical forms of the same element. That's important. Okay, so different physical forms of the same element. Keep that definition in your head. That's an allotrope. So what are they? I told you already. Diamond, graphite, and the new one that we discovered in the 1980s, Buckminster fullerene. There's more, of course, but we're only going to focus on three. There's graphene. Now this is where nanotechnology is taken over. Nanotechnology is working down here, all right? And this is where all the latest developments are happening in terms of medicine and in terms of catalytic conversions and in terms of organic synthesis. It's all happening down here, okay? But just for the confines of our course, we're going to focus on these three: graphite, diamond, and fullerene, or Buckminster fullerene. And I want you just to remember that in all three forms, it's only carbon atoms that are present. Okay, so let's take each one. First of all, let's take the diamond. Strongest substance known to exist. The strongest substance known to mankind. Right? There is nothing stronger, and we can only cut one diamond with another one. And there's the reason why. Every single carbon, and there will be billions of them, every single atom of carbon is bonded to 4 neighbours. Now you do that quick multiplication in your head, and you're talking about a huge exponential curve of a massive molecule, which makes this thing extremely stable. Yeah, Now, we also know that from going into places like the Play Barn or into Jack and Jill's where they have these climbing frames, you've got kids climbing all over them. Climbing frames are very sturdy because they're interlocked. Same thing here. This is a very, very stable molecule, highly stable. In fact, the hardest one we have, because of the fact that every carbon is bonded to 4 other carbons around it, giving you one huge macromolecule, which is the form of a crystal that we call diamond. Okay, since all carbons are bonded to 4 others, and all bonding sites are used up, the atom itself becomes an extremely strong macromolecule. The crystals refract light very well. Now, refract means it bends the light. So when light hits a prism and it bends, you get colour. All right. So when you allow white light into a diamond, only if the diamond is cut properly, and that's why it's an art form. You don't send your diamonds to be cut by Joe Soap down the road. You send them to the jewelers, particularly a gem master, and they will know, based on the diamond you give them, exactly how to cut that diamond to get the best refraction out of it so it sparkles at its best. So if you want a diamond to work properly, it's got to be cut properly in order to make sure that the refraction or the bending of the light gives the greatest sparkle. So that refraction there is nothing more than we talk about the sparkle. You know when somebody gets engaged and they kind of go, oh, I had a wonderful weekend, big ring, and you're taking the eyes out of your head. That's refraction. Okay. Graphite. Now, graphite is interesting because graphite is still carbon. However, graphite is carbon atoms arranged in sheets. So you've got one carbon atom attached to 3, and they form flat sheets which lie one on top of the other and hold each other together by very, very weak bonds. So the layers are being held by very weak forces of attraction, and as soon as you move them over something, they all separate and they stay on the paper. That's how the graphite or the lead in your pencil gives you the mark on the paper, because the graphite comes off very, very easily. It rubs off. All right. Because graphite has sheets and it's made up of sheets that are easily removable, it can be used as an industrial lubricant. So if we're drilling for oil and we're sending down metal pipes to grind rock and diamond faces to grind rock, we need something to lubricate that. Graphite is normally what's used in industry as a lubricant instead of oil. Okay, so graphite will conduct electricity since the carbon atoms are only bonded to 3. Now go back to diamond. They were bonded to 4. Now they're bonded to 3. What does that mean? Carbon has 4 bonding sites. In graphite, 1, 2, 3 are used up. Oh, there's one bonding site left vacant. There are some free electrons there. Remember delocalized electrons of benzene? Very similar here. So if you attach a cathode and an anode to a strip of graphite, it will conduct an electric current. Now, I remember when I was very, very young and I got my very first train set, as we did back in those days, and it was a beautiful CIE orange black diesel engine, which I was very proud of, and it was going around in a circle, and I was sitting for hours watching this thing going round and round in a circle, and at the same time, for some reason, I was breaking open a pencil, and I took out this little lovely bar of graphite. Didn't know what it was at the time, and for pure experimental reasons, I put the graphite over the track. Now, the track was electric. Now, I think electrocuted. No, the track was electric, but I put it down over the track, and the train stopped, and then took off, and the train went again. Put it back down. Train stopped. What did that mean? I knew that graphite and electricity were somehow related, and I learned that by just pure accident. Okay, messing. Now, I could have electrocuted myself, but I didn't. Put it down, train stopped, take it off, train started. Because when I put the graphite across the tracks, it took the electricity, didn't give it to the train, so it stopped. So graphite does conduct electricity. Okay, reason? Because every carbon only bonded to 3, leaving 1 free, meaning that there are some free delocalized electrons that are free to move. This leaves, as we said, an electron free per carbon atom, which is then delocalized, very similar to benzene, and can transmit a current through the substance. Layers, as we said already, they're covalent layers, so they're held together by van der Waals forces or London forces. So you've got sheets of graphite here, a sheet of graphite there. The force of attraction between the two, very weak van der Waals forces, because it's holding covalent neighbours together. And therefore we can slip off the layers very easily by dragging the graphite on a piece of paper. Hence, pencil marks paper. And the reason why we can get an eraser and rub it out is because the layers can lift off the paper. Okay, so it's interesting chemistry. Very, very simple chemistry as well. What do they look like? Well, that's them. So you notice every carbon, take this one here, is bonded to 1, 2, 3, leaving an electron free. This carbon here, 1, 2, 3, leaving an electron free, electron free, electron free, electron free. Get the idea? So up here, there's all these free electrons. Then there's the next sheet down here. So electrons are free. The one carbon has one free electron. Just keep that in mind. So there's plenty of free electrons to move should an electric current be put across this particular graphite. But these blue bars here, they're the very weak forces of attraction between the layers. They're your van der Waals forces, or your London forces, whatever you want to call them. So that's your van der Waals there, which are extremely easy to break. How do you break them? You just pull the layers away. Simple as that. Drag it over paper and they'll move away. Okay, so graphite, as we said, is used in pencils and also used as an industrial lubricant. So when you're drilling for oil, graphite is usually what they use to lubricate the machinery. And lastly then, Buckminster fullerene. What about it? What does it look like? Well, here it is. See that beautiful piece of natural molecular mastery? Yeah. Notice hexagon. 1, 2, 3, 4, 5, 6. Notice what's next door? Pentagon. 1, 2, 3, 4, 5. Exactly like the patches on a leather football. And by alternating hexagons with pentagons, we end up getting a fabulous sphere, which is a little cage that could be designed in the future to carry medicines from one particular area to a local area of the body to deliver, like for example chemotherapy and so on. So it's a fascinating piece of natural engineering, wonderful, wonderful molecule, and has great promise for the future. It has revolutionized science as it is capable of carrying chemicals within its center. All spherical molecules like this are called fullerenes. So it's not the only one. It's Buckminster fullerene, but it's not the only fullerene we have. We don't care about the rest of them. As long as you know one, you're fine. Okay, and they're under study at present. So we know this table. This is a junior cert table. We've done this before. What about metals and non-metals? So when we move away from the crystals now into the metals themselves and the non-metals, you've learnt this stuff already. You know your metals, okay? Metals are hard. They're shiny. Some of them can be hammered into shapes, okay? Some of them can be drawn out into very, very fine wires. The reason why we get extremely fine copper is because we stretch it. You don't make fine wires, you stretch copper into fine wires. Of course there's other metals you try and bring them apart, they'll snap. But a lot of them can be drawn into fine wires and they're excellent conductors. Now, what about non-metals? Just say the opposite. So just learn one column, that's all you've got to do. Hardness, by the way, luster just means shine, in case you're wondering. Malleability means they can be hammered, because the Latin word for hammer is malus. So malleability means they can be hammered into shape. Ductility means stretched. So if you're talking about stretch marks, talk about your ductile marks. Yeah. And heat and electricity, electrical conductivity. Well, metals will conduct. We know what conductivity is. Metals will conduct them. So metals are positive for all these. Metals are hard, most of them. Mercury is metal at room temperature, or liquid at room temperature. Don't forget that. Most of them are hard. Nearly all of them are shiny, except for the alkali metals, which have to be stored under oil and have a layer of oxide around the outside. Okay, but when you cut them, they're shiny. Most metals are hammered into shapes. A lot of metals can be stretched, copper being the typical example, and then all metals will conduct heat and electricity. What about non-metals? The opposite. Non-metals are soft, they're dull, they're brittle, they can't be drawn out, and they're very poor conductors of heat and electricity. Exception, graphite. Graphite will conduct electricity to a certain degree, so will silicon. Okay, so there are certain things out there, they're not metals, that will conduct electricity, but they're very, very few and far between. Okay, last couple of slides. Addition polymers. Now look, I just want to sum this up very quickly. Here's what I want you to remember. This is called, and I can all hear your heads, ethene. Good. If I take ethene with another ethene like this, okay, and another ethene like this, and I squish them under very, very high pressure, so extremely high pressure and a very, very high temperature, guess what happens? The double bonds open up. That double bond there, watch carefully, the double bonds open, so that double bond and that double bond and that double bond opens up, and guess where they go? They go between the molecules, which means you no longer have ethene molecules, but you've got a massive big chain of many ethenes. Now, many ethenes, the word from any in science and in English, poly, and in maths, yeah, polyethene. Polythene. That's where it comes from. So how did that happen? Take 3 ethene molecules. That's all I want you to do. Now it's going to be loads of them, so you'll have more over here and so on. That'll keep on going forever. Okay, just write down 3, put them together like that, high temperature, high pressure, squish them together, give them loads of energy, the double bonds open, they all link up into a massively big long chain, which we call many ethenes or polyethene, or to give it its nice name that we have, we don't say polyethene, we drop that E there and we simply call it polythene. And that's one of our plastics. But that is how we make every single addition polymer. So addition polymers are made from what? Usually from the alkenes. A-L-K-E-N-E-S. Usually always from the alkenes. Okay. Now, what do we have to know about them? Well, there's a couple of these things we have to know in terms of the examples of each. So, when you take the ethene molecules on their own, they are individual. Individual units are monomers. Okay, so an ethene molecule would be a monomer. So would propene and butene and pentene. They're all individual units called monomers. Mono means one. When you take monomers, shove them together under high pressure and temperature, the double bonds open, they all join up, and you get a polymer. And a polymer is a plastic. They join together by putting high temperatures and pressures on the monomers, opening the bonds to get polymers. Something like this. So there's your monomers, okay? And when you squish them under high temperature and pressure, so you've got high temperature, so a high temp and a very high pressure, what will happen? They'll all open their double bonds, link together, forming a very long chain of what were individual monomers, which we now call a polymer. Okay. So, polythene. Many ethenes. See that? Look at the brackets. Many ethenes. How do we make that? Well, first of all, let's look at the chemical reaction. And we've done this already. You take ethene, which is C2H4 with a double bond between the 2 carbons. You take a number of them side by side. You squash them under high temperature and pressure, and they open up and join together into an extremely long chain, which we call polythene. But it exists in 2 forms. 1, low density polythene, and 2, high density polythene. Now, most of you know from geography what high density population, low density population is. High density means a lot packed in together. Okay, low density means well spread out. So for low density plastic, we expect it to be very, very soft. And it is. Low density polythene gives me things like shopping bags and cling film. You know, the damn stuff that sticks to itself and to nothing else. You take it out and straight away it all sticks to itself. You try and open up, bin it, try to get out some more. It's like a magnet to itself, yeah? So that's cling film. And cling film and shopping bags, they're very, very soft plastic. And the reason why they're so soft is because the plastic is low density polythene. It was discovered by accident in 1933 using, guess what? High pressure and ethane, or ethene that should be, apologies, ethene. I'll check that and I'll check it for you and give it to you before I give it out. It consists of branch chains that do not pack tightly together, hence the reason why it's low density. It's soft and flexible, white waxy solid, chemically inert. By the way, all plastics are chemically inert. That means they don't react with anything. And they do not react with acids and bases either, and they are used in bags and cling film. What about the high density polythene? Well, if you shove a lot of molecules into a small space, the plastic becomes harder. And guess what? It's used for making things like buckets, okay? So bowls, buckets, baskets, and so on. But how do I get the low density to the high density? Answer, through a catalyst. A catalyst will cause the little monomers to pack together very, very tightly and then join up as a tightly packed polymer, which is a high density polymer, which gives you things like buckets and so on. And again, the same thing. The chains have few branches. They can pack tightly together. That means the high density, giving you heavier, less flexible, and a harder plastic. So buckets, bowls, baskets, etc. Okay, polychloroethene. Now, chloroethene is this. It's still ethene, but it just means that one of the legs of ethene has chlorine. So again, if you take, just to show you, if you take this one here, and let's take another one here, and let's take another one here. And I'm just going to do this a couple of times. I'm not going to do this for every slide. All right. And one of these legs is chlorine in each one. Okay. So there's just 3 random chloroethene molecules. Now, high pressure and high temperature on them. What happens? Well, this is what happens. First of all, pop, pop, and pop. And then, secondly, join, 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 and join. So you end up getting something like this. Huge big chain like that, and every second one has a Cl. Hence, that's called many chloroethenes, polychloroethene. Don't ask me why. Polychloroethene becomes PVC, polyvinyl chloride. So the only one that's PVC is the one that contains the chlorine, just in case you're wondering. Okay, and what about it? Well, there's the reaction. CH2 double bond CCHCl. So CH2 double bond CHCl. That's all we're saying, same molecule as before. Under high temperatures, 13 atmospheres, huge pressure, they join and they simply give you a string like this with every second carbon having a chlorine branch. Okay, so that's PVC. Now, a little bit of information on that. It's a rigid plastic used to make window frames and gutters, etc. It was also used to make false leather trousers when we were young in the 80s. All right, I remember a cousin of mine got a pair of leather trousers, real leather trousers, and I thought they were beautiful, and I couldn't afford the leather trousers, so I went out and bought a pair of PVC trousers thinking they were just the best, and they peeled after about 3 weeks. No use, I had to go in the bin after spending huge money on them. Anyway, looked cool for about 3 weeks, that was about it. Wouldn't look cool now, but looked cool back then in the 80s. And there it makes gutters. Okay, so gutters, window frames, anything that's very hard plastic, drains, etc. The hard plastics, that's your PVC. So when plasticizers, now plasticizers are things that soften a plastic. So if you take that very hard plastic here in the drains and in the gutters, yeah, if you add plasticizers to PVC, you get a soft version of PVC, which makes it very flexible and gives you lovely false leather trousers or raincoats or whatever, hoses, cable insulation, all that kind of stuff. It's the nice soft plastic that's used to insulate things or used to on the outside of clothes. Sometimes people have leather patches on their elbows. Yeah, those patches, they're not leather, they're PVC covered fabric patches, which are there just for wear and tear. So things like hoses like that, etc. Next one, polyphenylethene. Can I just remind you what phenyl means? Phenyl means the presence of benzene. Okay, so now we've got phenylethene. So let's have a look at that. Phenylethene, and it's polyphenylethene. So first of all, there is your benzene, as we said already, and there's your ethene molecule attached to it. So phenylethene. Now the way an organic chemist would tell you that is, no, that's an ethene molecule with benzene attached. So keep that in mind. It's an ethene molecule with benzene attached. So therefore, if you have this, I'll just take two of them. There. Let's take this one here. There. And let's put benzene on this foot. And let's put benzene on this foot here. Like that. Now, again, high pressures, high temperatures, what happens? That double bond there and that double bond there, they open and they link like that. So you get a long chain of what we call polyphenylethenes, which is known as polystyrene. And the polystyrene is the stuff that when we used to get new washing machines and new tellies when we were younger, we'd take the polystyrene, we'd run outside and we'd run it along the wall and we'd say it was snowing. Yeah, it's that stuff that kind of spreads all over the place. It packages, it protects things in transit. Yeah, so that's polystyrene. That's what we would call the expanded polystyrene. There's rigid polystyrene as well, which we'll talk about down in a moment. So another rigid plastic which is used to make yogurt cartons. So all the stuff that holds your yogurt or your little biotic drinks that you get, that you put into the fridge, that would be polystyrene, but it would be the rigid form. But when you pump this thing with hydrogen and with air, there's polystyrene yogurt cartons, polystyrene pens. When you expand this thing with hexane or air or hydrogen gases or whatever you're going to use, we get a very, very soft polystyrene. In fact, we get foamy polystyrene, which they put around washing machines and TVs in transit just to make sure that they're kept safe for protection against vibration and damage. It's very, very light. It's used as an insulator, but it's also used as a protector for things that are in transit. And there's the stuff. Do you remember that? Break it off, run across the wall, loads of little bits and pieces. Hooray, it was snowing. Could never stick together as a snowball, but there you go. Polytetrafluoroethene. Now, listen to that. Tetrafluoroethene. What's ethene? C. Tetrafluoro, F, oh dear, and F. Okay, so now what's going to happen? There should be F, by the way. Now what's going to happen? Well, if you've got another one here with 4 Fs, you can see exactly what's going to happen. Because when you put that over high pressure and high temperature, that bond opens, and what happens? They join, they join, they join. So you end up getting a huge big long chain with every single branch being one of fluorine, like that. So that is what we would call polytetrafluoroethene. Now, it has an industrial name, okay? It has a market name, and that market name is called Teflon. And Teflon is now used as an anti-sticking agent on the inside of your frying pans, on the inside of your saucepans. It's also used as an additive to clothes. Clothes that contain Teflon don't crease. Yeah, we also have politicians made of Teflon that nothing sticks to them, right? We used to call Bertie Ahern, the days of Bertie Ahern, he was known as the Teflon Taoiseach because there was so much trouble surrounding him, none of it stuck to him. So therefore he said he was non-stick, so he was the Teflon Taoiseach, okay? But Teflon, Roy Plunkett is known for Teflon. He was the guy who discovered it, again, by accident, yeah? But there it is, tetrafluoroethene. And tetrafluoroethene, when it's squashed together, forms a huge big long chain of carbons, and every branch then is simply fluorine, okay? And therefore the name for that, the industrial name, is Teflon. Discovered in 1938 by Roy Plunkett, it's pressurized tetrafluoroethene. It's a white, slippery solid that is inert to acids and bases and is insoluble. But its most, I suppose, widespread use is this. It's a slippery solid. Nothing sticks to it. You can do anything you want in a frying pan with Teflon, and you just tip it up and it falls out. Okay, so Teflon is a wonderful way to have an anti-sticking ingredient on the top of your frying pan or your pots and in your clothes to prevent creasing and then less ironing at the end of the day. It's used in non-stick coatings in pots and pans and so on, and it's also used in fabrics. Have a look next time you're looking at clothes. Some clothes will actually say includes Teflon, and Teflon is just to stop it from creasing badly. Okay, the last one, polypropene. Now what's propane? MEP, that's 3 carbons. And propene then will have one double bond like that. Here's another one. And now what happens? Well, in this case, again, we're going to have 1, 2, 3. We'll have 1, and then we'll have 2 here like that. 1, 2, 3, then 1, 2, and 1, 2 like that. But again, the same thing will happen. The double bond will open. So you'll get a situation like this. The double bond will open. There. And there, and then all these things here will simply join up like that, and that will join there, and that will join there, and you'll get a big long polypropelene. Okay, and polypropelene is the last of our plastics to look at, because polypropelene, apologies, somebody coming up, polypropelene, there it is, big long chain of methyl branches. The molecules are packed tightly together. They're strong and flexible, used to make bowls, buckets, beakers and chairs. Now, the beakers, those very strong beakers that you give to young kids, that's what we would say is polypropylene. Chairs and so on, the plastic chairs that kids sit on, polypropylene. In fact, if you make strands of polypropylene and then you weave them together or you braid them, you get a rope. And those things that people use as clotheslines, they are strands of polypropylene. Very tough plastic, and when you wind them together you get a rope of extraordinary strength. In fact, they can be used to tow cars, they can be used in order to carry quite heavy loads as well. Okay, so there's the bowls and buckets we're talking about, and then we've got fibers of polypropylene that are spun together to make rope, and there's the rope that we're all familiar with. So when you braid it or when you spin it together, loads of strands come together, interlock, and make something very strong. Okay, that's the entire chemistry course finished. Now, there's not an awful lot in there, but I would ask you, watch the video and make some notes as you go along. In Google Classroom, there are 2 sheets, and they're basically condensed notes. One is on your polymers, the other one is on your crystals and on your metals, okay? So it's just a matter of learning this. It's optional material, so therefore the chances of you answering it are quite low. You've got to answer 8 questions out of 11. 10 and 11 have 3 parts, out of which you have to answer 2, and that's where you're going to find the options. So therefore, there's usually the case where the questions are quite easy. They want people to answer this, and anybody who goes to the bother of learning it, they give them nice questions to be able to just regurgitate material. So in my advice, it's worth learning. Okay, and again, if you have any difficulties or need clarification on anything covered there, please let me know.